What's up, everyone? Welcome to Simulation. We are currently at NASA's IPAC, the Infrared Processing and Analysis Center. And as you can see behind us, we have a bunch of servers and data storage, and that is holding all of the infrared data and of the Spitzer Space Telescope and the Exoplanet archive data. And who better to be talking about exoplanets with than Dr. Jessie Christiansen? Thank you for coming on to the show.
Hi, Ellen. Thank you for having me.
And Jessie was also with us about a year and a half ago. We featured her. And Jessie rocks, and she's definitely at the forefront of categorizing and cataloging and taking certain exoplanets out, putting other updating ones. This is a really important part of space and part of science. And so we're going to be unpacking this for you. And actually, it's a very funny time because it's currently the ExoCal, which is the Exoplanet Conference in Southern California.
That's right.
And you have about 100 of these really prominent scientists in the exoplanet field that are congregating right now and talking about the field, which is exploding because Kepler has now had thousands of exoplanet discoveries, and now we're moving into Tess. Anyway, we're going to break that all down right now. Jessie has 5 years at the NASA Exoplanet Archive as a research scientist, where she's doing all of this cataloging. And why don't we talk about, because you did PhD in astrophysics and astronomy at New South Wales in Australia, and since then you've had this move to LA. You've been doing this 5 years now. Tell us about, you got two young ones that you got to mold their minds into the world. This is tough stuff, like balancing all of this out and being at the cutting edge of space. So maybe tell us a bit about the last 5 years in the space and how it's been.
Sure, thank you. Okay, so the last 5 years. So I moved from New South Wales to Boston for 2 years to do my postdoc at Harvard. Then I went to San Francisco for a few years to work on Kepler, and now I've been here for 5 years. Balancing finding planets and looking after my children is a tough act, I will say. But it's been a really exciting time in exoplanets. Exoplanets are really having this exponential growth in the number of planets we've found. You can actually follow it with time, and the doubling time is about 27 months. So every 27 months, there's twice as many exoplanets that we know about than before. And that trend, we think, is only going to continue over the next few years with the launch of Tess, as you mentioned, and later the WFIRST mission, which is going to launch in the next decade. So yeah, it's been a challenge, but it's been a super exciting time and a super exciting challenge.
Damn, so we're doubling the amount of exoplanets every 27 months.
That's right.
Wow, that's exciting, because it used to be zero.
Yeah, for a long time.
Yeah, and that was pre-2005 it was
1995.
1995, okay. Yeah, 1995 we were just we don't know what's really orbiting other stars, and now we're we know we know more, we know a little bit. Okay, that's crazy that we're gaining that many numbers, doubling every 27 months. That's crazy cool. And this seems to be now, it's Moore's Law. There's so many of these, biology is having sequencing drop in price now, that as well. It's so interesting how technology is helping us with this process.
It repeats again and again.
Yeah, across industries as well, which is very exciting. Exponential technology. Thank goodness. Okay, so let's talk just a bit about transit photometry. We're at the Infrared Processing and Analysis Center. Infrared is different than photometry, and so just being able to see on an infrared part of the spectrum versus being able to just see light. Maybe tell us a bit about maybe that difference, and then tell us about this transit photometry where you're actually seeing the light from a star drop because you see a planet orbit in front of it.
Sure. So photometry just means measuring light. So you can actually have infrared photometry. You're just measuring the infrared light. And you can have optical photometry, which is measuring the photometry in the optical part of the spectrum. So the way we find planets with, for instance, Kepler and now Tess is transit photometry. So what we do is measure the brightness of the star over and over again, and we wait for the little dip in the brightness of the star when a planet goes in front of it. Now that relies on the planet being lined up just right. So actually most planets don't transit, which means we need to look for hundreds of thousands of stars to find the small number that are lined up just right so that we can see them. So it's kind of an inefficient survey strategy, but it does mean we get to look at a lot of stars, which makes the stellar astrophysicists very happy.
And yeah, because you were just explaining that even though the star is here, the planet could be orbiting like this around it, not like this where it would go in front of our face.
Exactly. So if you were an alien civilization looking at the Earth, you'd need to be lined up in our ecliptic plane, which is where all the planets in our solar system are. There's the constellations of the zodiac. This is all our ecliptic. This is the plane of our solar system. If you imagine the solar system is like a big pancake, we're all in the pancake. So the alien civilization would need to be lined up with that pancake to see us transit. So that means we can only see a certain number of systems transit as well.
Because their galaxies are like pancaked in different...
Yeah, their solar systems are tilted. But the interesting implication of that is we know which stars could see us transit. We know which stars, if they had aliens around them, would be able to see us transit. And that's really interesting because those are the sorts of stars we could concentrate on looking for with, for instance, SETI and seeing hey guys, could we put something artificial in orbit to make an artificially shaped transit, which is one of the things we've talked about for signaling, like we're here.
Yeah. Okay. All right.
I feel like I just blew Alan's mind. He's just like, I don't even know where to go now.
Because just even thinking about the pancake shapes and how you have to be perfectly positioned, and so Kepler looked at 150,000 stars in one patch of the sky for 8 years, and then now there's this K2, the secondary mission that's going on with it, and about almost 5,000 or so at least identified, 2,500 confirmed, 2,500 more pending confirmation. 30 of these or so are in this habitable zone, that we think, which is very exciting stuff, could be like Earth, could have evolved intelligence or just microbial life, this type of a thing. But then there's Tess, which is just looking at the star systems closest to us, and so those are big differences. Looking really far away, or versus for a really long time, or looking close, just 1 month at a time.
Yeah, so Kepler and Tess really have different strategies. Kepler was a narrow, deep survey, like a cone survey, whereas Tess, which just launched in April, is an all-sky survey, but a shallow survey. So wide and shallow versus narrow and deep. And Tess is supposed to look at something like 10 million stars in the first 2 years for planets. So we're going to find tens of thousands of planets with Tess. We're really going to be able to keep going with our exponential curve that I was talking about and really find, exciting new things really nearby. That's the exciting thing about Tess is all the Kepler planets, as you said, are quite far away. The Tess planets would be effectively in our backyard.
And then what are we talking about regarding backyard, like 25 to 1,000 light years away?
More like 10 to 100 light years away. So, yeah, so the Kepler planets are 1,000-ish light years away. So even Kepler only really probed our local neighborhood. If you think about the size of our galaxy, the galaxy's 100,000 light years across, and we're about 30,000 light years from the middle. Kepler's only looked out to about 3,000 light years. So we've only searched like a little bubble right around us in terms of our galaxy. Tess is going to search an even smaller bubble, but we'll be able to study the planets that Tess finds in much more detail, which is the exciting part.
Yeah, yep. And then, okay, so now let's talk about what we've been finding, because as you catalog and archive these exoplanets, there seem to be some very interesting things that you've discovered as you're doing so. So teach us about that.
Sure. So, as we were talking about before 1995, we didn't really know about planets around other stars. And all of our theories about how we build planets, how we find planet systems were designed around our solar system, designed to find systems where you had rocky planets that were around our size and then gas giants that were around Jupiter and Saturn size. All of our theories were, how do we reproduce the solar system? But when we went out there... So egocentric. I know, right? When we went out there, we found everything but. We found this incredible diversity of different types of worlds. We found hot Jupiters, which is when you take a Jupiter-sized planet and you park it right next to the star. So it goes around its star every 2 or 3 days, compared to Jupiter, which takes 12 years. We found lava worlds, so balls of rock the size of Earth that are thousands of degrees, so hot that the surface must be molten. So it's literally like a little ball of lava traveling around its host star. We found compact systems of planets where you find 5 planets, all with periods shorter than 13 days. So in our solar system, Mercury is the closest planet, and it has a period of 88 days. This is 5 planets within 13 days. Just imagine how tightly packed those planets are. Yes. So we've just found this incredible diversity and nothing like we predicted, which is the exciting part, job security, finding all of these planets out there which keep us thinking and keep us imagining, keep us building new theories for how would you even create a hot Jupiter, for instance.
And I really like how the discoveries of planets orbiting stars, which every star has about at least one planet, and then about every 5 stars you'll find an Earth-like planet potentially. So I really like how this has a lot to do with simulation or running simulation, just because there's so many variables, and that you get thrown into all of these different styles of single star systems or binary star systems or hot Jupiters, or this is very exciting because it expands our mind's new dimensions of thinking and possibility. So I really like that aspect to it. So, okay, so out of all of the 5,000, then what are our trends that we're seeing? You were saying hot Jupiters. What are we thinking? Is there something like 1,000 of them are really far away from their star, or something like that?
Sure. So there are a few different trends that are emerging. One is that stars that have a lot of heavy elements compared to our sun seem to make bigger planets. So that's kind of interesting, and it might be intuitive, if there's more heavy elements, that makes, you can make a bigger planetary core, which then can accrete more gas, which ends up having a bigger planet. Other trends are that smaller stars seem to have more rocky planets around them. So M dwarfs are the new hot place to look for habitable Earth-like planets. So we live around a G star. Our star is just a big yellow G star.
That's funny, the gangster star.
Yeah, the OG. The OG star. I love it. But most of the stars... So so it's just this weird sequence, which has a very, nowadays, not very politically correct mnemonic for remembering it. OBAFGKM is the stars. So O stars are the biggest, bluest, brightest stars.
Like Vega.
Yeah, so and Sirius, so there's these big stars. And then, so our star is a G star, and then at the very end of that sequence is M's. So M's are smaller, they can be 10% to 50% the size of our sun. They're much cooler, so 3,000 degrees instead of 5,500 degrees like our sun. And something like 75% of the stars in the galaxy are M dwarfs. They're actually the most numerous kind of star. And the exciting thing about them is you can put... Yes. So actually, as far as we know, no M star has ever gotten to the end of its life, just given the age of the universe and how long M stars live for. All the M stars ever born are still alive. Whoa. I know, that's pretty cool. And it has really cool implications for, if they have habitable rocky worlds around them, that civilization could live for a really long time. Yeah. Every time I give a talk to school children about planets, someone's like, I hear that in 5 billion years the sun's going to expand, which it will. And, maybe we'll have solved other problems by then. But, if you were orbiting an M star, you don't have that problem for a very, very long time, even longer than 5 billion years. So we're excited about M dwarfs because it's easier to find rocky habitable planets around M dwarfs. The relative size of the planet and the star is much easier for us to see, and the planet can be much closer and still be habitable. Like in our solar system, if you took the Earth and moved it to the orbit of Mercury, it would be way too hot. There'd be no liquid water. We'd all, we live in Southern California, so we already know what that feels like. But that would be bad. But if we had an M star in the center of our solar system, we could get very close and still be habitable. So we could have an orbit of 2 weeks and still be habitable instead of a year.
Or if you had an O star, you could be where maybe Jupiter or Saturn is.
Yeah. Oh, so the interesting thing about O stars is they don't live very long. They, maybe a million years. So maybe that's not long enough. Yeah, they're quite, the big ones just come and go super fast. So maybe that's not enough time to develop life. Probably maybe you can't get life around O stars. So that's interesting. Yeah.
So there's another sweet spot with the size of the star.
Exactly. And the lifetime of the star.
Okay.
And the sort of radiation that it puts out. The problem with M dwarfs, we're going slightly off topic. The problem with M dwarfs is that they put out a lot more UV radiation than our sun. So the way life has evolved on Earth, UV can disrupt our DNA, it can cause mutations. And M stars put out thousands of times more UV radiation. So could you evolve life like our life if we were orbiting an M star that would, if we had very delicate DNA, our planets orbiting M dwarfs just sterile because we actually use UV light on Earth to sterilize clean rooms because it kills everything. It's bad. So this is one of the downsides of M dwarf planets. Like, they're easier to find, but maybe they're all sterilized because of the radiation. So that's an open question. We're still working that out.
Okay, so the trends are, one more time.
Okay,
on the trends.
Sure. So we find
Lots of M.
big planets around stars that have lots of heavy elements.
Yeah.
So stars that are the size of our sun can have a variety of amounts of heavy elements, from very little to a lot. Even though the star itself is the same size, the same temperature, looks the same, it can have a different composition. And so the stars where we see them have more heavy elements, they seem to have more giant planets around them, like Jupiter-sized planets. Another one is that M dwarfs seem to have more rocky planets around them. So systems like TRAPPIST. TRAPPIST is an M dwarf that has 7 rocky planets around it.
Yeah, all close.
Yes, all quite close. And so that's another one that we see.
And we see, like, out of the 5,000, is there about like 1,000 or so of these M dwarfs, or how many?
Oh, that's a good question. I don't think there's that many because there aren't a lot of bright M stars. That's the other thing about M stars, is they're all quite faint. I think most of the planets are actually around G and K stars. So our star and like 75% the size of our star. Okay. So most of them are around those. And that's mostly because Kepler found them and Kepler focused on those kinds of stars. Out of the 150,000 stars that Kepler looked at, only 3,000 were M dwarfs.
And then, that's a bit on the actual, like, cataloging and archiving. I think maybe you should tell us a bit about the process of taking a planet and confirming it. How many times you have to see it, dim the light before you confirm it, and then what it means to update it and retract it.
Sure. So when you see a dip, you get really excited. When you see 2 dips, you get very, very excited. And when you see 3 dips, you're pretty sure you know that it's a single transiting body, one thing that's going around 3, and you've seen it 3 times. So you're pretty sure. You want to see at least 3 transits. But still, all you know at that point is that something is transiting something. You need to know the masses of those 2 things to really confirm that it's a planet and not like a small star. Or you can have 2 big stars where one star is just grazing the bottom of the other star and causing a little dip, even though it's a very big star. So what we need to do then is go and measure the mass. And there's a few different ways of doing that. The most common way is to examine the star itself. So when a planet's orbiting a star, it's actually pulling the star around in a circle. In our solar system, Jupiter's pulling the sun around. So if you were, again, an alien civilization looking at our sun, you would see the sun trace out a circle every 12 years, which is the orbit of Jupiter. Exactly. So measuring the speed of the sun away towards you and away from you is measuring its Doppler effect. So that's what we do. We look at these stars and we try to measure their speed. Are they moving towards us or away from us? Are they doing it periodically? Is it the same period as the transiting thing we see? And then you can work out how massive the body is that's pulling on it, and that tells you whether or not it's a planet. So that's the most common way of confirming a planet. You want to see 3 transits and then go measure its mass, and ta-da, planet.
Okay, cool. And then that's confirmed. And then what about updated?
Sure. So usually as soon as you've got a mass, you publish your paper, you're good. But a lot of these planets we want to study more. We want to get better parameters. We want to find out more about their atmospheres, what they're made of. So often people would use bigger and better telescopes or get more data and refine the analysis. Or they'll come up with a new modeling method. That's quite common, like a new way of turning the data into parameters. And so then they'll publish updates. So one of the other things I do on the Exoplanet Archive is trawl all of the published literature for the best set of parameters for each planet. So people publish a new set and I have to look at it and look at our current set and be like, okay, these are better and here's why. The other thing that can happen is people go and look at this planet again and get more data and realize they made a mistake. Realize that what they thought was a planet, they'd actually misinterpreted something else, like stellar activity. The stars are also doing their own things, like rotating and flaring and all this kind of stuff. Or the transit that you saw was just a glitch in the instrument. It wasn't real. So then people publish retractions. So people say, okay, we went and looked at this planet again, and it turns out it's actually not there, so we should strike that one out. So part of my job, I'm kind of like the gatekeeper for NASA's Exoplanet Archive. I'm looking to see which ones I'm letting in and which ones I'm taking back out, which ones I'm updating. It's great.
Yeah, that's a really important job. Like you're saying, there has to be really solid evidence for it to be brought in, and it's good that that we're actually pursuing this like retraction as well. We're going in, we're double, triple checking. Okay. So what is so you were talking about what Tess is going to do and is already doing, looking at in a elliptical patch of the which way?
Okay.
Yeah. Teach us about that. And yeah.
Okay, so Tess has 4 cameras, and they make a big rectangle on the sky. Basically, the rectangle is about 90 degrees, so like a right angle. And it's about 25 degrees wide. So it's this big swath of the sky that it does in one hit. And then it rotates slightly and does the next one, and then it rotates and does the next one, and then the next one, and then the next one. And it's going to spend 1 year... 1 year doing that whole hemisphere of the sky. First it's doing the southern hemisphere, and then it's doing the northern hemisphere. Wow. But yes, each patch that it stares at, it's staring at for 1 month.
And it has so it's got one camera. So it's got,
so it's got 4 cameras, and this camera at the top is always on the pole, on the ecliptic poles. So as it's turning around, those stars at the pole are always being observed. So for the stars down near the ecliptic, they'll only get observed for a month because that camera will move around. That's right. But the stars at the poles will get observed for a year because that camera will always be observing them.
That is pretty cool.
Yeah, so we'll be sensitive to longer period planets at the poles than we are at the ecliptic.
Yeah. And then, okay, so then the actual size of Tess has got 4 of these cameras on it. So that means that by camera, it's not a mirror, or is it? There is a mirror on the back of the camera, and then it reflects the light onto a silicon again, and then
yeah. So 10 centimeter telescopes basically. There's 4 10 centimeter telescopes. Each of them is fairly standard optical design, but yes, it's reflecting the light onto 4 CCDs. So 4 different, and 10 centimeters, 4 inches. That's not very big. Because the point is that Kepler told us that planets are everywhere. Most stars have planets, as you said. And we only are looking with Tess at the brightest ones, the most nearby ones. So we didn't need a huge telescope. And that was one of the reasons why we were able to do Tess on the budget that we did it, was because you only needed little telescopes.
Oh, sweet. Okay. So, so we have certain candidates now that are like 10 to 100 light years away that we think are really high likelihood.
Yeah, so we have some very nearby planets that we're very excited about. For instance, our very closest star, Proxima Centauri, is 3.8 light years away, and it has a rocky planet in the habitable zone. So already our very closest star, planet right there. And Tess, just yesterday, brought out its first planet around a star that's only, I think, 12 light years away. So that's really close as well. So that's really exciting. Whoa. The point of Tess is to find all of our nearest neighbors. It's very exciting.
Find the nearest neighbors, and then further image them at a later time with James Webb and stuff like that. Okay, so a lot of the ExoCal conference that's going on right now is about detection to characterization. Okay, so now we've made detections, and now we're going to start characterizing them. You were giving us some characterizations earlier of M dwarfs and of very bright stars as well, that star spectrum, and then planets, some rocky, some hot Jupiters. Mm-hmm. Okay, so now as we characterize them, how do they even get filtered into the different buckets in the
Sure. So there are kind of gross demographic buckets that you can put them in, like this is big and this is small. But one of the exciting things that we're seeing now is we're starting to say, okay, if we take a bunch of the small ones, how do we divvy those up? What are the things that define them? And we can find groups like, oh, these all have a lot of carbon in their atmospheres, or these all have a lot of methane in their atmospheres. Like that's the level that we're getting to now, which is really exciting because now we're starting to understand the physics that's going on in terms of the formation processes and the evolution processes. Like how do you end up with an atmosphere that looks like this?
This is some crazy stuff because this is like, dozens of light years away and more. And how do we have the tools to be able to see what's in their atmosphere?
Oh, that's a really good question. So we have two ways of finding out what's in a planet's atmosphere. One is looking at its transmission. So when a planet is going in front of a star, the starlight will stream through the planet's atmosphere. At certain wavelengths, the molecules in the atmosphere will block the light. Those are the wavelengths that speak to those molecules. But at other wavelengths, the light will come through, so the planet will transmit light. So we can look at the light that gets transmitted by the planets and reverse engineer what molecules must be in the atmosphere of the planet in order to give us this signature, this spectrum of the planet.
That we're blocking the light.
That's right. So it's actually really interesting. The planet looks different sizes in different wavelengths because at some wavelengths, the atmosphere is full of molecules that are blocking the light, and at some wavelengths, it's transparent. So you effectively see deeper into the planet's atmosphere. So the planet, what we actually do is measure the size of the planet as a function of wavelength, and that's our spectrum. It tells us what molecules need to be there. So that's really cool. One of the other ways we can find out what's in a planet's atmosphere is the reverse. So when the planet goes around behind the star, right before it eclipses, or before the star actually blocks the light is being reflected off the planet's surface and back to us. And that tells us something different. So, it probes a different part of the planet's atmosphere, but it's similar in the sense that some wavelengths of light will be absorbed and some will be reflected, and that will depend on what molecules are in the atmosphere of the planet. So that's the emission of the planet. So we look for the planet's transmission and its emission.
And then the tool that is used for that is the same photometer?
That's a good question. We often use different tools for those because they're kind of in different wavelength regimes. So we've used the Hubble Space Telescope to do a lot of transmission spectroscopy. So this is looking at the light that goes through the planet's atmosphere. And we've used the Spitzer Space Telescope, which looks in the infrared, to observe a lot of the emitted light. And that's mostly because the emission is the strongest in the infrared. A lot of these planets that we're looking at are quite hot by virtue of the fact that they're often very close to their star, so that the light that they're emitting is very hot. So we can see them better in the infrared than we can see them in the optical. So they're actually different instruments, but they're both NASA space telescopes that we use a lot, Hubble and Spitzer. And when James Webb launches in a few years, James Webb will be able to do this in exquisite detail because it's a much bigger telescope, 3 times the size of Hubble, which means effectively 10 times the collective area. So it'll be able to really, really start to measure the atmospheres of smaller and smaller and cooler planets. So the cooler a planet is, the harder it is to look at its atmosphere.
Okay. So good. Okay. Maybe this is important to also talk about. The future of what we're doing with space. You were mentioning James Webb's going up with whatever it is, like 22-foot mirror.
Mm-hmm.
It's
6.5 meters.
6.5 meter mirror. That's so big. It's amazing. And then and it's gonna fold out all cool once it gets shipped up. That stuff's so interesting. Yeah. Let's get that thing launched. Yeah. And then there's all these other interesting sort of methods of blocking out the star light with star shades and coronography. So maybe teach us about that.
Sure. So the ways that I've talked about measuring planets and detecting planets so far have been very indirect. We're looking at the star and we're looking for the impact of the planet on the star. Either the planet blocks some of the starlight or the planet pulls on the star. One of the best ways, the clearest ways, the most unambiguous ways to look at planets would be to block out the starlight. So you don't see the star at all and you just see the planet. And that's very difficult because stars are typically 1 billion times brighter than the planet that's orbiting them. So that's a very difficult contrast ratio to measure. So we've come up with a lot of technical solutions to this where you try and block the wavelength of block the starlight from the star at certain wavelengths. And you can either do that, as Alan said, by launching a star shade, which is a very big thing that you launch far away from your spacecraft that blocks the starlight, but it's got this very specific shape, so it lets some of the light through, the light from the planet. Or you can actually put a blocker in your instrument, like a little coronagraph in front of your lens.
Wow. So these next sort of advancements in technology are going to enable us to image exoplanets much better.
That's the idea. We have this vision that in 20 to 30 years' time, we launch a spacecraft which is able to take the first image of an Earth-like planet around another star, actually see these planets and actually look at them. And that will be incredible. I mean, that'll give us the answers to many more questions than we can answer right now.
You guys heard it here first. Get that funding in for more space instruments as soon as possible. Okay. As we come to an end, I want talk a bit about space economy stuff. This seems like we're moving in the direction of more and more people. We were just announced the first person, the Japanese guy that's going to go in SpaceX's rocket around the moon. Bring some artists. Hopefully those artists can create inspirational works of art that can then inspire other people to care more about space and care more about the We Are One sort of effect on Earth. So what are you most looking forward to in the space economy? We already have all these small satellite companies and all this other kind of cool stuff. The ISS is having more projects come to it and all this kind of stuff. So what are you most looking forward to?
Sure. Well, I mean, even Tess has already benefited from the privatization of space. It was launched on a Falcon 9 in April of this year. So what I'm looking forward to is the privatization of space bringing costs down for launching exciting science experiments for us. That said, I don't want it to go too far. I would worry if space was left entirely to the hands of private companies that, then all of the goals and achievements in space would be very limited in scope. Like, it's fantastic that they're sending artists to space. That's great. And, at some point they're going to be sending miners to space to get asteroids and plunder all of their precious metals. But, so I want to make sure that there's a mix. A mix, I think, is the healthiest idea. So some privatization so that you can take more risks than, for instance, NASA can. Part of the reason why privatization is good is because NASA is spending taxpayers' money, so we can't be very risky with it because that would be terrible. But private companies can take more risks. They can be more, innovative. NASA's always launching technology that was actually perfected like 15 years earlier, which means we're never actually launching the cutting edge thing that's like exciting right now, because it has to be tested and reliable and probably planned into the proposal a decade early before it actually got selected and then tested and then funded and then built. But companies like SpaceX can be flying the latest thing. I just want to make sure that the public has a say as well in what's happening in space. Yeah.
And that we educate people to the extent at which we can make really good decisions about what's going on in space. You also, you were telling me about this before, but you were like, actually, I've been working on Tess for quite a while. It's not just since April, because it takes a long time for missions to get completely engineered and designed and then funded, and then actually doing the putting together of all of the mechanical and electrical and computational pieces, and then going out into space and then collecting the data. So this is a very, very long process that sometimes you'll only work on like 3 of these missions in your life or something like that. Question that we typically ask on the show. What do you think is the most beautiful thing in the world?
So I'm biased because I'm a mother of 2 twin 3-year-olds. So for me, the most beautiful thing in the world is healthy children and keeping them that way for as long as possible. Happy is good too, but healthy is the main part.
Yes. Happy and healthy kids, happy and healthy life. Yeah. That's a good one. And what do you think we can do to maximize the potential of especially young girls into our world?
So something that I feel really strongly about is the underrepresentation of women in the STEM fields. And that hurts everybody. It doesn't just hurt women. It hurts everybody because it means that we're lopping off at least 50% of our creative intellectual potential by doing this, by not exploiting everything that we have. So I think that starting as young as possible is the key. I was just telling Alan before, even at 3 years old, my kids are already being stereotyped, and that's very frustrating because at 3 years old they're still lumps and they're very moldable, and I don't want them to be molded into my daughter thinking I can't do science and my son thinking I can't cry. I want to. So just as young as possible, we need to be breaking these stereotypes, breaking these molds, not letting society condition our children into thinking that they have to be in a box. It's easy to say, but it's so pernicious. You just see it everywhere that this is happening. And I can't solve society's gender problem with one sentence, but just starting as young as possible, I think, and being aware of it and trying to step in when it happens. That's all I'm trying to do.
Yeah. This probably, I probably already know your answer, but do you think we're alone in the cosmos?
I don't think we're alone in the cosmos. I'd be surprised if we were alone, given the millions and billions of planets out there. I'm surprised we haven't heard from anyone yet if we are alone. Probably my gut is that there is microbial life commonly throughout the galaxy, but there's some reason why we never get to be a galaxy-faring civilization, and we don't know what that is yet.
And do you think that potentially we are in a simulation?
I don't think we'd be able to tell, so it's kind of a meaningless distinction. It's a fun question, but it doesn't change anything if we are, because we wouldn't be able to tell, because what kind of simulation would that be? So it's fun to think about, but I don't think we can tell.
And this has been something that's been on my radar now for just a little while, this idea that as a civilization becomes so intelligent and they get to the singularity, that they just go inward, that they don't want to go outward. They can travel the cosmos technologically, simulation-wise, maybe, rather than actually going and physically doing it. Do you think that might be an answer to the Fermi Paradox?
It could be. I don't think we have a way to rule it out yet. I don't think it's the only answer to the Fermi Paradox. It's kind of one of the more depressing ones. It's only slightly less depressing than we nuke ourselves in the next 10 years. Like maybe every intelligent civilization just tears itself apart, which, given that it's 2018, it's not looking too unlikely.
I tagged you in that one, remember? I tagged you in that one on Twitter when I said that, isn't it likely that they just don't know how to work together if they evolve intelligently, and they can't figure it out because there's just too much war and hate instead of that love. And then just, do you think we have to reach a zoo hypothesis? We have to reach like teleportation or something for them to start talking to us because they don't want to ruin the evolutionary experiment?
That is really hard to speculate about because we don't have any information. We haven't seen an example of that on Earth, given all of the different types of things that we've seen. We've never really held back from colonizing, have we? So it's hard to imagine, but obviously if it was an alien, if it was truly alien, we would have difficulty imagining it anyway. And I mean, we already see it in our own solar system. We already want to get out there to the next planet, to the next thing. We're going to Europa now, and it's like, where does it stop? So it's hard to imagine that could be the answer, that we're in a zoo and that we're just being left alone to evolve. The prime directive version, that's tricky. In part because I feel like we'd have seen evidence of something by now if there was a giant galactic civilization out there just kind of holding back. Yeah. It might just be that the laws of physics are brutal and it's really hard to explore interstellar distances, and people just kind of realize that they can't in an efficient way.
Yeah. That is a lot of exoplanet cataloging and archiving and analysis. Good times with Jessie Christiansen and the NASA Exoplanet Archive and Cataloging System. There's still so much to discover with Tess out there now, and even with all the data that we have, now it's time to image the atmospheres, and we're very grateful because we'll have Stephen Kane on the show in a little bit. Yes. So we're really excited for that, and to chat with him a bit more about actually understanding the habitability, and that will be very exciting. So thanks, everyone. Thanks, Jessie. Thanks you for coming on the show. Greatly appreciate it. Huge thank you.
Thanks, Alan.
And everyone, thank you for tuning in. If you guys had a good time, let us know what your thoughts are below. We'd love to hear from you. Don't just consume this content. Go and create with it. Go and make art with it. Go make music with it. Go make videos with it. Go start businesses with it. Go and start cool stuff. Go create. Thank you, everyone, and we'll see you soon.